Next talk is by Wang Intel Corporation. So the talk title is a distributed MLPerf ResNet50 training on Intel Xeon architectures with TensorFlow. So please start screen sharing. Wang.
Okay. Thank you, Professor Hanava.
Yeah.
So let me share the screen. Okay, share my desktop. Share. Okay.
Yeah, I can see. Yeah.
Can you see?
Perfect.
Okay. Yeah. Okay. Hi everyone. My name is Wang. I'm a software engineer at the Intel Corporation, based in Santa Clara headquarters. My area of focus is on TensorFlow product optimization, and with the area of focus on distributed training. So prior to joining Intel Corporation, I was a graduate student at the University of Delaware, where I obtained my PhD. So today, my colleague and Niranjan and I will be presenting our MLPerf ResNet50 results running on Intel Xeon architectures with TensorFlow. As you have heard from the previous talk, John mentioned the Intel Xeon is our foundation of HPC and AI, and we will be showcasing what we can do with our foundation CPU. So before we proceed, Niranjan, I want to give a short introduction to the audience here.
Hi everyone. My name is Niranjan, and I work with Wang on TensorFlow optimizations. And as part of this work, we also worked on enabling BFloatló16 DataType with TensorFlow, which we will be covering during the presentation. And my background is, I think, similar to Wei. I did my PhD from Stony Brook University in New York. And I work on optimizing TensorFlow for Xeon CPUs, high performance computing, as well as some background in compilers and graph optimization for TensorFlow. So yeah, okay, by the way.
Okay, thanks, Niranjan. So I will start with some introduction and background, focusing on MLPerf. Right now, it's more known as ML Commons, and also a quick refresher on the deep learning, and also a quick introduction to what is the Intel-optimized TensorFlow. Okay, so for MLPerf, it's a benchmark. As you can tell from the name, it's a performance for machine learning covering. At this point, I will say the deep learning. So it has a training track and inference track. So we were focusing on the training tracking here. And in the training benchmarks, there are several models across different areas of vision, language, and reinforcement learning. So and others. So for today, we'll be focusing on the computer vision, the very popular image classification task, which is using ResNet50 v1.5, testing it on the well-known ImageNet dataset with an accuracy target of 75.9% of accuracy. And this is just like a simplified view as a refresher of what is the training and inference workflow looks like. So the input is starts from a lot of labeled data, which are usually batched, say hundreds or thousands of images in a batch, and go through the network or the forward and calculate the loss, and you generate the error, and you backprop the according to the error, you back propagation. You get the gradient, and then it's an iterative process. So in the middle, as a part of the MLPerf training workflow, we're required to also run inference, which is to check the training progress. So how well is your model right now? So where at one point, say in the middle of the training, it will freeze and save the model weights, and then feed the inference and validation data set, and check the output and accuracy. So it goes on repeatedly until we reach the predefined accuracy threshold. Okay. So for this, running with ResNet50 model, we are using Intel-optimized TensorFlow. So Intel has been working on optimizing TensorFlow for a few years now. So so far, a lot of our Intel optimizations are already featured in the mainstream, which the Google's TensorFlow GitHub page. And the source code are in there. In addition to source code, we have Intel has released all the different kind of binaries that people can use. There are PyPy wheels. You can just do pip install. At this point time, I want to emphasize it's a pip install Intel dash. In future, we're trying to get this merged into the default TensorFlow as well, where people can get Intel optimized version just by doing pip install TensorFlow from Google page. Okay, and in addition to PyPy, we also have the Docker containers available. So people when they have Docker, they can just pull that and get Intel optimized TensorFlow. And of course, in addition to that, we have Anaconda channels. And so if you really want to do some customization or even want to build from source, and there's a way to add to build it from source, but at this point we want you're reminded that we need to add this specific flag. Yeah, but if you don't want to build from source, we have Intel has released the binaries for you to try. Okay, so that covered the introduction and background. So, but before I go to the hand over to the next section to Niranjan talking about BFloatló16, I want to emphasize that what the main performance drive engine underneath TensorFlow is the oneAPI deep neural network library, short name oneDNN. So you have heard John talking about oneAPI being one our like a key strategy to be the to form a good ecosystem for people to adopt Intel hardware and using Intel software. So this for Intel optimized TensorFlow, we build upon the oneDNN. So on the left side, you're showing, actually this picture is showing the stack. So on top of the CPUs, we have the oneDNN library. By default, it's within Google, it's the eigen library. So it's basically an alternative to that. So it's oneDNN is customized for Intel architectures. So and sitting on top of that is the majority of our team who like integrate all the to call the oneDNN APIs within TensorFlow, right? And in order to do that, sometimes we need to do I think it's to some degree similar to the presentation that we just did, right? We just saw like array of structure versus structure array within the deep learning field. We also have some sort of some concept of a data layout. So in order to make it run faster, we might need to adjust the data layout, NCHW or NHWC convergence. Okay, so this is the kind of a recap of the software stack that provides in optimized performance with the Intel optimized TensorFlow, where the main engine is the oneDNN, part of our oneAPI. Okay, so the next section I'll hand over to Niranjan, and he will talk about the BFloatló16 enablement. So Niranjan, go ahead, and I can help you navigate through the slides.
Yeah. Mm-hmm. Yep. Thanks, Wei. So as a part of this work, we also worked on optimizing and supporting BFloatló16 DataType within TensorFlow's framework for MKL and for Intel CPUs. And we also used ResNet50 as a proof point to demonstrate that BFloatló16 indeed can converge to the same accuracy as Float32 for training process, and that it can deliver better performance than Float32 on Intel's latest generation of Xeon CPUs. So just a introduction to what BFloatló16 DataType is. Essentially, it's a floating point representation, but in comparison to floating point 32, the difference between FP32 and BFloatló16 is that BFloatló16 uses less bits per mantissa, As you can see, it uses only 7 bits for Mantissa, whereas FP32 IEEE format uses 23 bits for Mantissa. But then the number of bits for exponent remains same. So what that essentially means is that the range for the floating point numbers remains same, but the precision represented by BFloat16 reduces as compared to float32. And this format was introduced by Google's Brain team. And this was essentially introduced specifically for deep learning workloads, where they observed that reducing the precision is perfectly fine for models to converge. The loss of accuracy does not really matter for convergence issues. Um, I think it's an observation that is specific to deep learning workloads, and I'm not sure at this point like whether that generalizes to HPC workloads in general. But FP16 was an intermediate step before BFloat16 was introduced. But FP16 actually uses a different number of bits for exponent as well as Mantissa, and that leads to issues in terms of model changes that are required to use FP16 format for training or for inference. And BFloat16 is a lot simpler in that sense that converting floating point 32 number into BFloat16 is as simple as dropping the lower 16 bits of the FP32 number. So, and also theoretically speaking, it basically gives 2x improvement in terms of memory access saving as well as bandwidth savings. And we'll see in our performance analysis as to how much it gives really with the real workload.
Okay.
So this is basically just an introduction to BFloat16 type, and it has gained popularity in terms of hardware support. Initially, Google was supporting this with their first version of TPUs, and it is still there. And also, Intel also recently supported BFloat16 with the third generation of Xeon CPUs, which is codenamed Cooper Lake. It was launched last year around April and May time. And it is part of this technology called as DL Boost, which is basically contains support for BFloat16 instructions. And essentially, there are 3 new instructions being added as a part of DL Boost. So 2 of those instructions convert a single pack data into BFloat16 data type, whereas the third instruction is essentially just a dot product of BFloat16 pairs that accumulate into a pack single precision. So we use Cooper Lake or the third generation Xeon CPUs for our performance evaluation also. Now, before we go to the evaluation section, just a brief introduction to how we enable BFloat16 within TensorFlow. So essentially, if you recall the diagram that Wei or the stack that Wei showed, the CPU backend calls into the library that we use, or oneDNN library that we use. And this is a piece of code here, which is actually called as kernel in TensorFlow's stack that calls into the oneDNN API directly. And since the kernel, since TensorFlow's use C++ templates, supporting BFloat16 type was very much simple. We just had to add one more registration for the BFloat16 type for the operators that were supported by oneDNN library. So in a nutshell, registering or supporting BFloat16 type with MKL backend was as simple as just one line change into the kernel registrations. Can you go to the next slide?
Okay.
But we also had to do a few manual changes on the ResNet50's model, the Python model. And conceptually, those changes are also pretty much simple. We had to basically keep the activations or the gradients in the BFloat16 type, whereas the weights that are used for training purpose were kept in float32. And this is the standard procedure that is followed for enabling mixed precision data types or BFloat16 data types in deep learning. So essentially what we did was to use TensorFlow's cast API, which is a Python API for casting tensors from one type to another type. And we introduced this casting tf.cast operator between the layers that support BFloat16 and between the layers which do not support BFloat16. So input to the layers that support BFloat16 are casted to use BFloat16 type, whereas the output is converted back into float32 type. And once we did that, the only other thing that we had to do was to cast the input images also from float32 into BFloat16 type. And this was required because MLPerf ResNet50 uses ImageNet data set, which uses float32 type for input images. So by using tf.cast again, we converted those images into BFloat16 type. And then TensorFlow uses the type propagation on the model. So once the input to the model is converted into BFloat16 type, all the subsequent layers or the operators in that model operate in the BFloat16 type also. So these were the manual changes that we did. But fortunately, now Google has introduced this feature called as AutoMixed Precision. And it's still an experimental feature, but the idea here is to do these changes to the TensorFlow's graph automatically rather than doing it manually to reduce the user's burden. So essentially, in a nutshell, the way it works is it modifies the TensorFlow's graph, the low-level graph representation that you use for a Python model, and then it automatically figures out which of those graph nodes can operate in BFloat16 type, and then it will introduce the casting nodes before and after these operators that operate in BFloat16 type. And we also support AutoMixed Precision with MKL backend. We have written a blog post about it, and it talks about how to use AutoMixed Precision with Intel-optimized TensorFlow and how to get it running with Cooper-like hardware also. So feel free to check it out if you're interested. It's a very simple two-line change into the Python model that you need to do to exploit BFloat16 data type within your model.
Right. Okay. Yeah. Thanks, Niranjan. If you recall, like this involves a lot of topics like BFloat16, ResNet50, and our newest Cooper Lake and Intel-optimized TensorFlow. But one element, remaining element is how do we do distributed training. So in here we leverage the communication library released by Uber. It's called Horovod. So the advantage of this software library is that it is compatible with the TensorFlow source code. And in order to leverage it, you don't need to do any code modifications within TensorFlow itself. And the Horovod and Uber, they take care of all the communications so that we can leverage directly Intel-optimized TensorFlow with BFloat16 integration and with the Horovod code together. And with that, we observed that on the model side, to use Horovod, it's only a few lines of a change and instrumentation, and then everything will be in place, and we can do benchmarking. And it's a good alternative to TensorFlow's native distributed strategy. Yeah. So these are just an example of how we did the ResNet50 model changes. So the key Horovod APIs are highlighted in here. So it just start with the initialization, kind of starting a MPI communication word, and we need to be updating because we are doing training. We need to update according to the number of workers, the corresponding global batch size. Basically, your problem, how the batch that I show in the beginning of the refresher of the deep learning training and inference workload. So it dictates how much amount of work is per step. And also you need to shard or divide the data set among the different workers, so they get randomized yet not non-repeated data set. So in the middle, you would call Horovod API to wrap around the distributed optimizer over the original TensorFlow optimizer, and some logistic calculations here. And one more thing is that you would need to broadcast like kind of a synchronization point where you broadcast all the variables from rank 0 to the other ranks. So other than that, so we found that, so because the MLPerf training not only requires improve the optimized and the distributed training, but also on the validation data set as well. The validation task, which is that kind of you have come to a training point, and now you want to all the workers to stop and then do the switch into an inference workload and see what's the inference accuracy. So initially, actually during our submission, we did not yet enable this feature, but the feature is that the workers can actually also divide the validation data set instead of repeating the entire validation data set like in parallel. So they actually can divide the work and say you have like 128 files containing the validation data set, and you have like 32 workers, and each one can just access four of them, and in the end, still leverage Horovod and call a reduced API to get that. So this is one technique that we used to improve further the overall time to train, because it includes both training performance and distributed inference performance. And I'll quickly go over the typical distributed TensorFlow setup. And usually we install TensorFlow first and then install Horovod. The prerequisite is a certain version of MPI need to be in there. And then you will launch the MPI command to specify how many hosts, how many nodes you want to use, and how many sockets you want to use. And quickly to the, we will first show the single node multi-socket benchmarking and the convergence results, and then we'll also touch upon the multi-node the studies. Okay, so this page was actually when we launched the product Cooper Lake, as Niranjan mentioned last year. This is how this is actually the representative results from enabling BFloatló, which is a new feature for our latest Intel Xeon processors. We're observing up to like 1.93 times. The theoretic is like two times, as Niranjan mentioned. So we were able to, with Intel software optimization and oneDNN, we were able to get this for both training and inference. And in addition to ResNet50, we have the natural language processing, which is a popular use case as well. We are accelerating up to here 1.9x. So so when it comes to the real training performance where we submitted to MLPerf, these are the results. So MLPerf requires 5 repeated runs, and you get the Olympic average, where you get rid of the highest and lowest and calculate the average. So we were able to actually, to our knowledge, as you probably have known, like a few years ago, like on Intel Xeon, it would take probably more than several days to do it, but right now we can do this within like 20 hours. So, and further we improve that using the technique where we can do distributed inference. So initially our unoptimized, well, it's optimized but not optimized for inference, is that everyone is doing the validation for the entire data set, and it was the inference itself, it took about like 1100 minutes. After enabling the distributed inference, it came down to about 5 minutes. So, and overall time is just to get a little bit lower than 1100. Yeah. So that's the single node multi-socket. So actually we are also tested multi-node training and see how whether Intel-optimized TensorFlow and BFloatló actually works. So in here, I'm showing two graphs. In here, it's actually a direct snapshot from a popular tool from TensorFlow world. It's a TensorFlow TensorBoard profiler, where the top one shows the top one accuracy going from the start of the training to the end of the training, where I think the orange one is the IP32, where we use the original IP32 data type, and BFloatló is the one we enabled with BFloatló using 256 ranks in here. So and then and you can see the mostly overlap, and the accuracy in the end was surpassing the accuracy threshold. And interesting to know that this is what the specific learning rate schedule that MLPerf community used for ResNet50. It is called the LARS, layer-wise adaptive rate scaling. So these are the details we achieved. We used up to 256 workers. Okay. So I think I'm approaching the end of the presentation. So conclusion that we used the oneDNN backed Intel-optimized TensorFlow. We have a BFloat16 integration, and we applied the distributed training techniques using Horovod communication library, and experimented on our foundation of HPC and AI, which was the third-gen Intel Xeon Scalable processors, and applying the MLPerf latest optimizer with the ResNet50, and we were able to actually successfully submit MLPerf training and was featured as one of the entries. And thank you, everyone. Any questions for Niranjan and me? Yeah.
Thank you very much for your talk. So any questions from audience? So I would like to confirm your experimental setup. So yeah. In the distributed training, you used 256 ranks. So how much is okay, number of machines is 64. So
yeah, here I can I kind of one quick over this. I can explain in more detail. At that time, so the first set of the results where we submitted to MLPerf, it was 8-socket machine that we submitted, but it was only one node, 8-socket, but it was in distributed fashion where we used 16 ranks. So each socket in that case we used 2 MPI ranks, so a total of 16 workers in that case. So for this one, it is a larger scale. So actually, at that time, we were not having the Kubernetes system, the 3rd gen yet. So we did this for the purpose of verifying functionality. We did not focus too much on the performance side. We're just trying to confirm with this larger scale, BFloatló will still perform similar to IP32. So we had access to our 2nd generation, which was Cascade Lake. So we have 128 of them. Those are dual socket machines that we experimented on that. Ideally, we could have done that on the same machine, but due to some cluster management or conflict, we had to switch it to a different cluster, which is in similar configuration, but it was a specific, it was 2nd gen Cascade Lake as well, but it was special in that it featured double the amount of cores in each socket. So it was so therefore I only needed to use 64 of them to get 256 workers, because I have so this 64 will still have 2 sockets and a total of 128 sockets, but each socket is featuring double the amount of the double the amount of the 82 60s. So the total core count, they are still the same, but it was arranged in different number of machines. Yeah.
Okay, and so what kind of the MPI library in the Horovod?
Oh, okay. So it's actually Horovod is built on top of MPI, so it doesn't it itself it calls into underneath into the MPI routines. So it supports Intel MPI and also OpenMPI. So it itself is just implementing the majority part is the ring all reduce part. So it leverages the existing MPI products available to the general public, OpenMPI, Intel MPI. Yeah.
Yeah. So actually in your experiment, what kind of the?
Okay, we actually used OpenMPI. Yeah.
Okay.
Yeah.
So I'm not sure about OpenMPI, but so if the Intel MPI, so Intel MPI has many kinds of algorithm for each so API like or reduce or some kind of yeah. So in the OpenMPI case, how about algorithm in the already used
Okay,
work?
so yeah, that was all taken care by Horovod. So at the so what we can guarantee usually that we we first make sure that one socket performs well with Intel optimized TensorFlow and with the oneDNN, and then we leverage we add a stack on top of Intel optimized TensorFlow, the Horovod. So the Horovod, the library itself within itself, it was designed in an efficient way that it's already like the users distributed TensorFlow like a ResNet50 model users, they do not need to worry about the specific tunings, and then it's already, you just need to worry about how do you want to specify the number of workers, how do you want to specify, do you specify the number of cores dedicated to each worker, and then the communication part, it's all taken care by Horovod, and it was shown to feature very good performance actually, even with out-of-box testing. Like if you have that environment set up, it's automatically gives good scalability from our testing. Yeah.
Okay, thank you.
Yeah.
So any other questions in short? No? Okay, thanks to speak again.
Yeah, thank you very much.
Thank you very
I will
much.
stop sharing.
Yeah. So this is the end of the first session. So we will have a 20 minutes break, and we will resume the next session at 11:15. So the invited talk by Joe Curry.